Can you all hear me well? Am I audible now? Okay. Okay, before starting today's topic, I want to clarify one thing. Some of you asked me about that rounding of error about this topic. In the last class, we have solved one problem that was round off 2 by 3 or get the approximate value of 2 by 3 and then find its absolute error, relative error, etc. Now there we get that the value is like this 6, so it becomes 0.6666, this one, okay, and we rounded it off up to fourth decimal place and we wrote it like 6667. Now some of you asked me that it should be 6666. So now I just want to recall the rule. At first I found that I said something and I wrote something else, so this is because the whole confusion occurs. So let me clarify one thing, that is how to check whenever it is given that correct it up to 4 decimal place or correct it up to 4 significant figure. Then we just have to take this number, this is up to 4th digit, put a line there. Now check this n plus 1th term. Okay, if this is greater than 5, then add plus 1. Okay, if this is less than 5, then keep it unchanged. And now the problem arises when it is equal to 5, that is the n plus 1th position is equal 5, then the problem occurs. Now what happens if it is equal to 5? Then check the nth position's number. If it is even, then keep it unaltered, that is keep it unchanged, and if it's odd, then add 1. Okay, so in this case, for the approximation of 2 by 3, the n plus 1th position is 6, which is greater than 5, so we add plus 1 with the nth position, that is 6 plus 1 7, so it becomes 6667. Okay, that was the actual rule. I guess in the last class I said something and I wrote something else, so this is why whole confusion occurs. Now moving to today's topic. Today's topic is solution of algebraic and transcendental equation. Algebraic and transcendental equation. You all are familiar with algebraic equation like polynomial x to the power 5 plus 4x cube plus 6 equals 0. This is an example of an algebraic equation like polynomial functions. This type of equations are called algebraic equation, and if in that equation there are some other functions also added like some trigonometric function sin theta cos theta, or some logarithmic function log x or e to the power x, such type of functions if added in that type of equation, then it becomes a transcendental equation. We don't know how to solve that type of equation, transcendental, but we are quite familiar with algebraic equation. Now here in numerical analysis, in this chapter we will learn few methods. There are total 4 to 5 methods in the syllabus. We have to discuss it all of the methods one by one. The main object of all the method is just to solve the transcendental equations, but we cannot actually solve them. We can approximate their result. That is, we can at first found a place where the root can occur, then we will apply successive procedures, a particular procedure, to get to nearer to that root. That is, we want to get one approximate value of a particular root. Maybe it is correct up to 4 significant figure or 5 significant figure, like that. So the first procedure we have in our syllabus is called method of bisection. Method of bisection. From the name of this method, obviously we can say that the middle point will occur here, as it is the method of bisection. We are bisecting some interval. So what we have to do, suppose we get, the method is, suppose we get fx equal to 0, one transcendental equation. Then at first, by tabulation method or by inspecting method, we have to find out one interval, naming the interval as a0, b0. Okay, such that we have to find this interval a0, b0 such that f of a0 and f of b0 have different signs. That means one is positive, another one must be negative. That is, always we have to find a0, b0 such that f of a0 into f of b0 is less than 0. That means it should be always negative. Both the signs should be different. Now after finding this, suppose this one is our a0 and this one is our b0. Now then after that, check the value of f dash x in that interval. If it keeps the same sign, if f dash x keep the same sign throughout this interval, then by using Bolzano's location of roots theorem, we can claim that between that point a0 and b0, the equation fx equal to 0 has a root. Right? We have already learnt about Bolzano's location of roots theorem. That is, whenever f of a0 into f of b0 is less than 0, that means there exists at least one root of the equation fx equals 0. And now with that theorem, we are adding one more condition, which is f dash x keeps the same sign throughout the interval. Then that at least root will be replaced by one and only one root. That means if we found one interval a0, b0 such that f of a0 into f of b0 less than 0 and f dash x keep the same sign throughout the interval, then we can claim that fx equal to 0 has one only root in that interval. Okay, so this is our first procedure of method of bisection. We have to find out this interval. Now after finding this, we get this one. Here we will bisect the interval. That is, we will find the middle point of that interval, taking the middle point as, suppose, x1. Then what will be the value of x1? It is, as it is the middle point, it will be a0 plus b0 whole divided by 2. Now consider the sign of f of x1. That is, check the sign of the functional value of the function fx at the point x1. Now it can be positive, it can be negative, right? And f of a0 can be positive, can be negative, and f of b0 can be negative or positive. Now we have to choose either a0 x1 or x1 b0. Accordingly, the sign should be different. That means if a0 is positive and x1 is negative, then we will choose this interval a0, x1. And if x1 is positive and b0 is negative, then we will choose the new interval x1, b0. That means according to the sign of x1 and a0, b0 of the functional value, we have to choose either a0, x1 this new interval, or then x1, b0 this new interval, such that f of a0 into f of x1 less than 0 and f of x1 into f of b0 less than 0. Then we will create the new interval. Let us consider the first interval. Suppose we get the sign at the two endpoints are different here, so we are choosing this interval. Then again we will apply method of bisection here, taking the middle point, naming it as x2. Then x2 will be a0 plus x1 whole divided by 2. Then again check the sign of the function fx at the point x2. If it's positive, then take the first one, or if it's negative, then take the whichever interval is having the different sign on the end point. Suppose a0 is positive and x2 is negative, then take this one, or x2 is positive, x1 is negative, then take this one. Depends according the sign of the end points. Then we will create another new interval, and we will apply this procedure until we get the right approximation of our root. Okay, so this is the procedure of finding root by applying bisection method. So I am starting giving one example. You have to find out the root by applying this method. It will be clear once we solve few examples. Okay, so starting, write down example 1. Compute one root of sin x equal 10 into x minus 1 of sin x equals 10 into x minus 1, comma, correct to 3 significant figure. Correct to 3 significant figure. Compute one root of sin x equals 10 into x minus 1, correct to 3 significant figures. Now from this equation we can easily say it's a transcendental equation. It is not an algebraic equation because there is the appearance of this sine function, trigonometric function. So it's a transcendental equation. As we are taking let fx equals sin x, putting all of this in one side. So sin x minus 10x plus 10. This is our required fx. We need to find out a perfect approximation of one root for f, which is correct to 3 significant figure. Now for that reason, what is our first step? First step is to find that interval a0, b0, right? Where f of a0 and f of b0 have different signs. So starting with x equals 1, that is starting with a0 equals 1. At first compute the value of f1. Use the calculator and get the value of f1. Put the value x equals 1 and get the value of f of 1. Plus 0 point, what have you written?